Let's talk about first order, constant coefficient, linear, ordinary differential equations. Okay, I know this is a very long name, but let's just break it into pieces. Before we begin, our dependent variable is y and independent variable is t. So we are just using t instead of x. So first order is basically just the first derivative and second order is just the second derivative. So we have the highest derivative that we have is, for example, second one in the second order. Let's talk about linear. So we know that ax plus b format is like a line. So we know that this is linear. So how can we relate that to the differential equations? So this is just an example. This is linear. But for example, this one is not linear because of the squared thing. These squares here mess up everything. So you might ask, what are these then? This is also squared, but that's our independent variable and that doesn't count in this case. So that would be just considered as a coefficient. So you might also ask, then we also have a square here. How is that linear? I'm gonna just put a question mark here. We will talk about that at the end of the video. So I'm just gonna copy the example right over here. So it would be constant coefficient when we have no t. So t is changing, right? It's our independent variable. So when we have no t, then this is going to be constant coefficient. So we can have some constants, a, b, c, for example. So what about this term ordinary? It is when we have one independent variable. If we have more, then that's going to be partial differential equation. For example, we would have this, but we are not going to deal with this, of course. So for this video, we are going to be dealing with stuff like this. Okay, let's do an example. So this is our constant. We are just not going to use a, b, c. We are just going to use tau. And we have some initial conditions. At t equals 0, our y is y naught. So this is our initial condition. And so our y equals this. This is not a guess. We know that for a fact. And I will prove that in the end. So I'm just going to put a question mark here and we will prove that in the end of the video. So if we know y equals that, then we just plug it in there. So let's do that. We first take the derivative. We are going to make a common factor. So we know that e to the lambda t won't equal to 0. And the only way to get a 0 would be through this. So this would be our characteristic equation. And this would be our lambda. So you might have noticed that I skipped writing a's here because we had the a here. The reason is because when we make a common factor, we would end up having the a here, and that would create some unnecessary steps. Like right now it's simple, but in the future when we go into more complicated stuff, that's going to create some problems. So we're going to just write this constant in the end. I'm just going to keep it there for you so you don't get confused, but keep in mind in the next videos I won't write that constant in the steps. Here I want to mention something. You don't divide out the e. So don't say we cancel out e because we have 0 on the other side. Never do that in anything. So for example, you are trying to find the roots of this solution. And you end up cancelling out the x. So you have one of the roots, but you're missing the second one. So this is the improper way to do it. The proper way would be doing it this way. So now you didn't miss one of the roots. So you don't do such a thing here. I know that that won't equal to 0, but just keep it a habit and don't cancel out terms like that. Okay, so we found lambda. So then we can now plug it in the question. And this is our general solution. We are going to use the initial conditions to find the specific solution. So we had the initial conditions. So therefore a equals y naught. So now we can write the specific solution. Okay, let's sketch this. We are missing something. It's called PTC, process time constant. And that equals 1 divided by absolute value of lambda. We found our lambda to be this, so we plug that in the equation and we and we find the PTC to be tau. So what does this mean? It is the time it takes for the exponential to get to e to the minus 1 its value. I can explain that easier on the sketch. So if we have our y naught over there from here, this will decay and will go to 0. But what the PTC says is that assuming 1 divided by e is approximately 1 over 3, we can say when y naught gets to its third of its value, that is basically tau. So when we reach to tau, y naught is 1/3 of its value. So as you can see, this decays to 0. So it is stable. So this would be a transient. So the transient is going from a state to another. And it decays to 0. This would make more sense in the next videos where we have particular solution. But for now, just keep in mind that this is like a transient. Okay, let's expand on the idea a little bit. So what different cases do we have? So we saw this one, it was decaying to 0. So this is stable. And we have this one. This one explodes. It goes exponentially up. So this is unstable. This one forgets about initial conditions. This one doesn't. So for the stable one, if you started from here on or here or here, you'll end up getting to 0. So it kind of forgets about the initial conditions. But this one doesn't, and it's unstable. We have another case, which would be like a oscillation. So this one would be marginally stable. We would say this one has no damping. So this is a second order ordinary differential equation. More on this later. So don't worry about this one. We will talk about this on later videos. One last thing I would like to mention is about this name homogeneous. So we call this a homogeneous problem because we have the 0 over here. So this is unforced, natural. You can almost imagine the right hand side input to the system. So anything that doesn't have y going to be on the right hand side, and anything that has y in it will be on the left hand side. So the right hand side will be our input. So now it doesn't make much sense, but in the next videos that will make more sense to you. Okay, let's now talk about the question marks. So we had a question mark over here. How is this linear? So if our y will be in terms of meters and dy dt will be in terms of meter per second as the velocity, and the second order will be in terms of meter per second square, you can see that we always have this meter, but it's not being squared. Like I said, we don't look at the power of the independent variable, so we only look at the power of the dependent variable right now for differential equations. So then if the power of the independent variable is just 1, then it's linear. And here we can see the independent variable's power is just 1. Okay, let's talk about the other question mark we had. So how do we know if this is for a fact true? So you remember we had this in the beginning, right? So let's now solve this instead of just plugging this into the equation. So we would send the y to the other side and bring it here on to the bottom, and we send the dt to the other side, and we also send this one to the other side, and we end up with this equation. So now if we integrate both sides, we will get ln y plus a constant equal to minus t divided by tau plus another constant. So this is just a coefficient, and we would get minus t divided by tau. So now if we move this constant to the other side, we would just have another constant. And now to get rid of this ln, we would get everything to the power of e. So we would basically just do this. And we would just get this as y. So y equals e to the minus t times e to the c. So we could just separate them, right? And now you can see that this is also another constant. E to the c is just another constant, so we would have this. And now here is what we had in the beginning. And if you remember, lambda was just -1 divided by tau, which is, yeah, basically the same thing. So in the next video, we are going to talk about the non-homogeneous solution. Basically, the same thing we had, but instead of having a 0 on the other side, we're going to have something here. Thank you for watching. Independent. Why I can't say this word?
Independent.
It's so hard. Why is it so hard?
Independent.